Hey guys, in this video we're going to be looking at calorimetry. Within this video we should be able to achieve the following learning objectives. We should be able to restate the definitions of calorimetry, calorimeter, heat capacity, molar heat capacity, and specific heat. And we should be able to use the following equations in order to perform calorimetry calculations. And lastly, we should be able to do bomb calorimetry problems. So calorimetry is the idea of measuring heat flow. So it's the measure of heat flow. And we measure heat flow using a calorimeter. So a calorimeter is the device for measuring heat flow. So the device used to measure heat flow. Okay. And if we have a constant pressure system, which a lot of our calorimetry is done at constant pressure, we're looking at delta H. So delta H is our heat flow when at constant pressure. If we are not at constant pressure, then we're looking at just our Q, okay? And when we're looking at this, our normal calorimetry, what we're going to be mainly focusing on, our calorimetry will measure the delta H for a reaction or process. Over to the right, this is what we call a coffee cup calorimeter. It is a constant pressure calorimeter, and we look at how the aqueous solution, which would be in here, how that changes as a reaction is done or a process is undergone in that coffee cup calorimeter. Okay. So let's look a little bit at heat capacity and specific heat. So first, when we add heat to a substance, that substance will get hotter. So when heat, our energy form, is added to a substance, that substance gets hotter. And more heat, greater temperature change. But it's not just the amount of heat that's added that determines the temperature change. The heat capacity of the substance also will determine how much change in temperature you have. So the magnitude of the temperature change will, of course, be dependent upon how much heat you add, but also upon the heat capacity. The greater the heat capacity, the more energy that's required in order to heat a substance, and the more that substance holds on to that heat. So greater heat capacity leads to more heat is required to heat, or required to raise the temperature. Of the substance. And the more that substance holds on to heat. Okay, you can kind of think about this if you think about a sandwich versus a bowl of soup. So if you heat up a sandwich and a bowl of soup to the same temperature, you're going to find that your bowl of soup is going to take a lot longer to cool down than your sandwich. Now, this has to do, of course, with how much surface area is the substance is actually exposed to, but even more than that, a soup is going to be mostly water, which has a very, very high specific heat. And then bread is going to have a very, very low specific heat in comparison. So your bread is going to cool down much quicker than your soup will because of the high heat capacity or specific heat of that substance. Okay, so we define our heat capacity as the amount of heat required to raise a substance temperature by 1 Kelvin or 1 degree Celsius. Heat capacity, simple C. Amount of heat needed to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius. They have the same difference in their degrees, right? If you change by 1 degree Kelvin, you're going to change by 1 degree Celsius. So those are going to be interchangeable within heat capacity. Okay? And then when we're talking about a substance's heat capacity, it could either be a molar heat capacity or a specific heat, depending on what unit of substance we're using. Okay? So this is our equation for specific heat. Specific heat is heat or quantity of heat transferred in joules divided by mass of substance in grams, and our temperature change in either degrees Celsius or Kelvin. You do not need to change the temperature. Okay, you're going to be looking at a change in temperature, and the change will be equivalent whether you're in Kelvin or degrees Celsius. Okay, so specific heat, this is going to be given as C subscript S. We can also have our molar heat capacity, which is going to be slightly different. It's one going to be C subscript M, but instead of mass, it's going to be moles. So it's going to be joules over moles times by Kelvin, or joules over moles times by degrees Celsius. Again, these are interchangeable. Okay, here is some specific heats of substances, and we almost always use specific heat. There will be times you'll use molar heat capacity, but to use one versus the other, you just need to convert from grams into moles, or moles into grams. It's very easy. So our specific heats themselves, we have things like nitrogen gas, which is a reasonable temperature or reasonable specific heat, but then we have things like water that has a very, very large specific heat. Note, please, that the specific heat is going to be phase dependent. So water in the liquid state is going to have a different, very different specific heat than water in the gaseous state or water in the solid state. Okay. Let's try an example. It takes 487.5 joules to heat 25 grams of copper from 25 degrees Celsius to 75 degrees Celsius. We want to know what the specific heat is of copper in joules per grams degrees Celsius. The equation we use is Q is equal to mass times by specific heat times by delta T. Okay, so this is our heat, this is our mass, our specific heat, and our delta T. So it's just a rearrangement of this equation right here. Okay, and it's just, you could use either one. This is just the form that most people are familiar with. There's also the form if we have our molar heat capacity. It's going to be moles times by our molar heat capacity times by delta T. But we are talking about grams in this case, so we're going to use this equation right here. So we have 487.5 joules. That is our Q. And then we have our mass at 25 grams. And then we have our change in temperature. We're going from 25 degrees Celsius to 75 degrees Celsius. So our delta T is going to be final minus initial So 75 degrees Celsius minus 25 degrees Celsius, giving us a 50 degrees Celsius temperature change. Okay. Now, we're going to put all of this into our equation here. So we've got our Q, 487.5 joules, equal to our mass, 25 grams, times by our specific heat, which is what we are solving for, and times by our delta T, 50 degrees Celsius. Okay? And when we solve for this, we get a specific heat equal to 0.39 joules over grams times by degrees Celsius. And for a metal, it's very reasonable to have a specific heat that is less than 1. We should know that metals in general are going to heat up very, very quickly, very, very easily. That's why we use them to cook with, right? They very easily heat up once heat has been applied. Okay, let's look real quick at what's called constant pressure calorimetry. That's what we're going to be most familiar with. So this is when we keep our pressure constant. So when a reaction is done in a calorimeter that is kept at constant pressure. So in the case of our coffee cup calorimeter, which we looked at just a little bit ago, our coffee cup calorimeter is a constant pressure calorimeter because it doesn't have anything that's holding this down, right? So if some gas evolves during this reaction, it can push up that cork stopper in order to release that and keep a constant pressure system. Okay, so all of our coffee cup calorimeters are going to be constant pressure calorimeters. And our coffee cup calorimeter itself is the most common constant pressure one. So most common constant pressure calorimeter. And we use it in order to determine our heat flow. Okay, so what's happening is we're carrying out a reaction in an aqueous medium or a process in an aqueous medium. So a reaction or process is carried out in an aqueous medium. During this process, we're measuring the temperature of the water. So the temperature of the water is monitored. And as the reaction or the process is taking place within the aqueous solution, as it's taking place within the water, the reaction is either absorbing or releasing heat, and we're looking at the heat that is absorbed or released by our system, by what we're observing, by looking at the temperature of our water. So we observe the temperature change of the water, which is our surroundings, to gain information about the system. So this is going to be our reaction or process. Okay, and we're still going to use the same equation that we've already used, where we use Q equals mass times by specific heat times by delta T, unless we're in moles, then we use the one with the moles. We're just going to take into account that we're monitoring our solution, we're monitoring our surroundings, we're not monitoring our reaction directly. So first we have to keep in mind that our Q of our reaction will be equal to the negative Q of our solution or water. The reaction and the water or solution will have different sides, opposite signs, because as the reaction releases heat, it's absorbed by the solution or water, or vice versa, if the reaction absorbs heat, it absorbs it from our solution or our water. So we will usually, since we're observing the water directly and we're indirectly looking at a reaction, we'll find what the temperature change of the water is and then solve for our Q of our water using our specific heat of our water. So our Q of our water will be equal to our mass of our water times by the specific heat of our water times by our change in temperature of our water. So we'll look at that Q of our water and then we'll put it into this equation to solve for the Q of our reaction. Okay. We also have something that's called constant volume calorimetry or bomb calorimetry. And it's called bomb calorimetry because it is calorimetry that's performed in a bomb. So this is a calorimetry experiment where we're doing a combustion reaction. So a combustion reaction is carried out in a bomb calorimeter. It is a calorimeter that can withstand extreme pressures. So here we do not have a constant pressure system. We have a system that's going to produce a lot of pressure, actually. But this is a very accurate method for determining the energy of a reaction. In the case of constant volume calorimetry, we're actually looking at our internal energy instead of our enthalpy, because we do not have a constant pressure system. Internal energy instead of enthalpy. Okay. And we can do this because since there's no change in volume, there's no work, so our delta E is equal to our Q at a constant volume. So no change in volume, no work. Our delta E is equal to our Q at V, which is our constant volume. Okay. And what happens, the way that this works is we have a known compound with a known energy, and it's used to determine the specific heat of the calorimeter itself, and then that value is used to determine the heat of an unknown. So first step is to determine the calorimeter constant, so C calorimeter, using a known substance. And then after you know what your calorimeter constant is, you can solve for your Q of your reaction by setting it equal to the negative calorimeter constant times by the change in temperature of your water. So let's try an example. So we have 0.194 grams of quinone in a bomb calorimeter. The initial temperature of the water within that calorimeter is 25 degrees Celsius, and after the reaction, the final temperature is 28.20 grams. Assuming that the heat capacity or calorimeter constant that was gotten using a standard is 1.56 kilojoules per degree Celsius, we want to calculate the heat of combustion of quinone in kilojoules per mole. So with our calorimeter constant, this is going to take into account the water along with the calorimeter itself, so it should take into account all the heat changes that are occurring due to the change in temperature of the quinone. So our calorimeter constant is equal to 1.56 kilojoules per degree Celsius, and our change in temperature is equal to 28.20 degrees Celsius minus 25.00 degrees Celsius, final minus initial, giving us 3.20 degrees Celsius. We can then put this into our equation. Q of our reaction is equal to negative C calorimeter times by our delta T of our water. So our Q of our reaction is equal to negative 1.56 kilojoules per degree Celsius. We don't need to change this out of kilojoules as we want our answer in kilojoules anyways. And then multiply that by our temperature change, 3.20 degrees Celsius, and we get a Q of reaction of negative 4.99 kilojoules. And this is per the amount of sample we have. So to actually solve for our internal energy, we're going to take our energy that's produced during this reaction, divide it by our grams of our sample, so 0.194 grams of quinone, and this will give us negative 25.7 kilojoules per gram of quinone. And then we can convert this into kilojoules per mole by using our molar mass of quinone, where 1 mole of quinone has a mass of 108 grams. We could just solve for our molar mass using our chemical equation above. Okay, and then when we solve for that, we get negative 2,780 kilojoules per mole. Okay, guys, that is everything. I hope you guys understand a little bit more about calorimetry. I'll talk to you guys later.